Well, at this point, we've learned much of the basic Java code that we need to solve many different kinds of problems. Really that's what programming is all about, is problem solving. So the remainder of the semester, we'll be learning how to organize our programs better, use a few more of the Java API functions in order to organize data, and use file I.O. Well, at this point, we've learned much of the basic Java that we need to know to solve many different kinds of problems. That is what programming is all about, problem solving. The remainder of the semester, we'll be learning how to organize our programs better, use a few more of the Java API functions, for example, how to organize data and use file I.O. This problem is typical of many that we'll need to solve. We're asked to solve many similar type of problems in the same program execution. The problem would be easy if we could write three programs to solve each one of the individual problems. But the solution is not to run the program many times with different input, but to run one program. So let's examine the code. Well, the programmer elected to implement this using three for loops. And we see that the body of the loop is the same regardless of the values we want. We want to add and output a message that is similar as well. So what is needed as a solution is to make our code more general in nature, code that we could reuse to solve the same problem with a variety of constraints. For example, to sum from 45 to 60, or from negative 15 to negative 35. In this solution, also notice that the for loops don't start at 0 or 1, something we may have overlooked during our study of loops. Well, the solution is to create a method that will sum any range of numbers. We do so by defining a method. We create methods as a way of being able to reuse code. The highlighted code at the top is our method, and it doesn't look much different than the code highlighted in the body of main, and this is where we use our method. Method code is not executed automatically, as is our code in main. As programmers, we need to tell our programs to execute methods as we need them. You've already been using methods: math.pow, math.random, system.out.println. These are all methods stored in the Java libraries. Many programming organizations create custom libraries of their own methods as well. So in essence, between the Java libraries and the custom libraries, writing programs becomes less complex, because much of the complex work can be completed by the use of methods. In this chapter, we'll look at how methods are defined, particularly by looking at the anatomy of a method, called its signature. When we say define a method and declare a variable, we're making a subtle distinction here. By defining, we are describing what an item is or does. A declaration usually involves allocating memory to store data for the declared item. We'll also discuss how some methods require input, as well as the differences between methods that return a value, sometimes called a function, and methods that do not return a value, referred to as void methods or sometimes procedures. You've been using methods for a long time without giving second thought to it, particularly value returning methods, functions. Using methods is like a black box. You're not concerned about how the method does its work, only that if you give it the right inputs, you'll get the right results. Consider the calculator. If you enter a 9 and then press the square root key, it will return a value of 3. Do you care or know how it arrived at its answer? No. You just care that if you give it the right input, it will return the right results. If you give it -9, it will only return an error because it's expecting positive integers. So what you've been using on a calculator is a method, a function. Once we learn how to define methods, we'll look at how they can help us organize our programs so they're easier to maintain, easier to debug, are modular in their design, and we can share or reuse our methods with other programs. Well, a method is defined by its signature, and you've been writing the main method for several weeks now, and main signature is main, the method name, and then in parentheses you have string args. Well, string with the square brackets means it's an array, and we have named the array args. So args is really a variable that main can use. Public and static are its modifiers. We'll discuss those in a later chapter. And void is the return type. That is, main does not return any values. Now, main is a special method in that the Java virtual machine looks for a main method in order to know where to start executing code. If you write a program without a main method, it is not executable. So if we look at our self-defined methods, we see that the header contains a signature that looks very similar to our main method. The signature starts with the two modifiers, okay? An accessor modifier called public, which makes the method available for use, and a static modifier, which we'll learn more about in later chapters. For now, always start your methods with public static. If you forget to say public, that is the default. The modifiers then are followed by a return type. So if you're writing a value returning method, sometimes called a function, then the return type will be one of the data types we've already learned about. If your method will not return a value, then the return type is void, hence called a void method, or sometimes a procedure. Next, you'll need to select a name for your method, and it should be meaningful. And by convention, methods names start with lowercase, and use the camel casing notation if it's multiple words. What follows are the formal parameters. The formal parameters are the input data the method is expecting to operate upon. Now, not all methods require formal parameters. For example, when you use the random method, we didn't pass any data to random. So it just depends on what the method is designed to do. Defining the formal parameters uses the same syntax as declaring variables. That is, a data type and a name, followed by a comma if you need more than one formal parameter. What will be important to the programmer when she or he wants to use the method is the method's name, the number of parameters it requires, their intended meaning, the data type of each parameter, the order in which the parameters need to be specified when using or invoking the method. The names we use for the formal parameters should be meaningful and are only known to the method. Consequently, they are of no concern to the programmer that uses the method. Remember, the method is a black box. So our method named max has two formal parameters, both integers. The remainder of the method's definition involves writing the code to accomplish its given task. In the case of our max method, it is to determine the larger of the two integers. Notice the body of our method. It has all the elements of a Java program, including its own variable declarations, int result, and notice also that the code body knows about the formal parameters as num1 and num2. The last thing of importance is a new Java command, return. If we're writing a value returning method, we need a way to pass that value back to the using program in the same manner as math_random returned a number that we could use. So it's important to remember that a value returning method or a function can only return one and only one value. When we invoke a method, we use its name followed by a set of parentheses. If the method has no formal parameters, the parentheses are empty, in the same way as when we invoked or called math.random. Notice in this example of invoking or calling max, the actual parameters are x and y. They contain the data that the max method is going to use to determine the larger of the two. Note also, there is no relationship between the names of our actual parameters and our formal parameters. We can also use literals as our actual parameters. The code at the top defines our method to compute the miles per gallon. It takes two formal parameters, the miles driven and the number of gallons purchased. So our definition demonstrates also that we can return the results of an expression just as easily as returning a variable. So we have our definition of miles driven 1,000 and gallons purchased as 50. What will be the miles per gallon after we invoke our method? Did you say 0.05? Well, that seems very unreasonable. What's the problem? Well, the actual parameters are specified in the wrong order. The function has no knowledge of the meaning of the actual parameters. It simply knows that it must divide its first formal parameter by its second. Well, what is the result now that I have specified the formal parameters in the correct order? It should be 20. In this example, we've used the output of the method to set the value of a variable. Well, this example demonstrates that we can use the value returning methods, or functions, any place in our code where it would be legal to use a literal. And finally, example 3 here demonstrates the use of a method as if it was a statement. In the same manner, we have been using system.out.println. However, most programming languages will not let you use functions in this way. Void methods, or procedures, are designed to be used as statements. Functions are not designed to be used as statements. Let's take a look at the operation of a program that invokes or calls our max method. The actual parameters when calling max in line 4 above are the values I and j. They become the values used by max as num1 and num2. When main encounters line 4, the values of I and j are passed to max. Max's code is executed, and finally the result is returned to main, where k is set to the value of 5 in this case. So let's watch it in action. At this point, control is being passed over to the max method. Max's code is beginning to be executed. Max is returning the results to main. The value of k is set to 5. At this point, the max method still is available, but it stays dormant until we may need to use it again. So I hope this little animation gave you kind of a sense of what goes on and how control is passed back and forth between the calling program and the method. Well, you need to study the method under panel A for a little. All right, it will throw a compiler error and with something that says that the return is unreachable. Since n is less than 0 is redundant, because if I had simply had the else statement in there, it would accomplish the same thing. So the compiler throws an error thinking that the 3 if statements can be false, and therefore there is no return as a default. Well, assuming our max method was defined in a class named testmax, the code above shows the reuse of our max method. You need to be sure at this point that the new program class and the testmax class are in the same folder, or at least that you use the full path name to where to find testmax, such as c:\projects /testmax, etc. In practice, programming organizations will have developed custom libraries where the custom methods can be added to those libraries, and then they can be imported in the same manner that we've used to import java.util.scanner. You'll find the testmax program on page 158, listing 5.1. The next slide demonstrates that you are not restricted to simply one method per program. Well, this example demonstrates two things. First, I have defined more than one function. Max is defined at line 8, and min is defined at line 17. The next thing that it demonstrates is that unlike the listing in 5.1, I have defined my functions after main. The key point is that functions must be defined within the class boundary. So my functions must be defined within tester, right? So this class has 3 methods, main, max, min. Their order is unimportant. They all have their own set of enclosing braces to delimit the beginning and the start of end of the method. Each time a method is invoked, the system stores parameters and variables for that method in an area known as a stack. As shown in the slide, each method has its own stack area, and as methods are executed, they need to reserve memory for the variables that are needed. In the case of a called or invoked methods, the memory areas are reserved as program code declares the variables. The memory or stack for that method stays intact until the return is encountered, or if it's a void method, it's until the method exits through the method's closing brace, at which time the stack space for that method is released and the variables are no longer available. The following animation should be instructional. First to be declared and first into the stack is I. Next, J is declared. Control is being passed to the max method. Control and the result is being passed back to main. Note at this point, since max is finished, max's stack is cleared. Variables are no longer available. The print grade method is an example of a method that does not return a value, called a void method. Its return type is void. We sometimes refer to a void method as a procedure. In general, the print grade method is fine for demonstration purposes, but convention usually follows a rule that functions or procedures that are being designed for reuse should not be producing output. That is the rule for the calling program. This example is more professional, and getGrade accomplishes the same thing. However, the output of getGrade is more usable. Main is being used to produce display output. However, another program, a different main, could use the output from getGrade, say, in order to just count the numbers of A's and B's, etc., and then put out messages regarding the counts. Actual parameters or arguments are what make methods capable of solving the same problem but under different circumstances. The argument list used in invoking the method must match the formal parameters in order, number, and compatible type as defined in the method signature. Now, compatible type means that you can pass an argument as a parameter without explicitly casting it, such as passing an int value when a double parameter is expected. But you can't pass a double when an int is expected without explicitly typecasting the double to be an int. When we pass arguments, we are passing them by value. We are giving a method a copy of the calling program's variables. The copies are then stored in the method's designated formal parameters. The second and third panels above show that the swap method changes the values of its parameters, but as the last panel shows, the values in main have remained unchanged. So pass by value means that methods get a copy of the formal parameters. When we modularize code, we use methods to solve the very complex pieces of a problem. Consequently, modular programs are easy to read. It makes the main part of the code easy, since long code sections are replaced by simpler methods. They're easier to write because individual components can be individually written and tested. We can use methods developed from other programs that have already been tested, and new programs can use methods that we may have developed for this program. And modularized programs are easier to debug and maintain. So there's a lot of advantages to modularizing your programs. So modularity and top-down program design go hand in hand. This problem to convert an integer to hexadecimal is implemented in section 5.7 in listing 5.8. Hexadecimal is base 16. It's another one of those numbering systems along with binary that computer professionals like to use. Hexadecimal, hex for short, digits include 0 through 9 and then A through F. So if you count the digits, there are 16 of them. The conversion algorithm requires that we can convert the remainder of a decimal value with remainder 16 to a hex digit. After we get this hexadecimal digit, we build a string from left to right of these digits. We have to use a string because we're going to be using alphabetic characters as our digits. And then we adjust the decimal value again by dividing by 16, and we repeat the process, right, until the decimal value is 0. Using an organization chart as shown in the slide is a convenient way to decompose a problem into the smaller pieces. You continue this decomposition until you get to one of the lower blocks that solves an individual piece of the problem. The upper blocks control or invoke or call the lower blocks. Well, when considering modular design, we have to be assured that each module meets the following criteria. First of all, completeness. If we take all the modules as a whole together, they completely satisfy the problem specifications. They solve the problem. Cohesiveness is a very important concept in that each module must perform one and only one task. And in coupling says that the paragraphs or the modules, the methods that are used do not depend on how the other modules have been implemented. They're only connection, they're only related through the data that is passed back and forth. These three blocks of code show the implementation of our modular organization from a previous slide. They also demonstrate the three properties we just discussed that modules must exhibit. Note that the only connection between the modules, coupling, is the data that's passed back and forth. We have cohesiveness, since each method does only one thing. Convert decimal to hex computes the remainder mod 16 and passes that value to convert to hex digit, where the appropriate hex digit is returned back to convert decimal to hex to assemble the hexadecimal string. Once the decimal integer has been completely converted to hex, the string value is passed back to main, in this case for printing. And we have completeness because taken together, the three modules solve the complete problem. This example demonstrates the reuse of the convert decimal to hex method, as well as it begins to introduce the idea of abstraction. It emphasizes the concept that implement details of convert decimal to hex are hidden. That is, the using program does not need to know how the method accomplishes its work. It only needs to know the specifics of input and output requirements. The author of convert to hex could change the implementation code that does the conversion without requiring any change to this using programmed test conversion. So using methods are like black boxes. We don't know what's inside the box, the implementing code. We only know that if we put the right things in, we should expect the correct results out.